You're listening to Cool Air Hot Takes.
Welcome to the second episode of Cool Air Hot Takes, a brand new podcast about anything and everything from the world of buildings, HVAC, and energy.
You may be asking yourself, what are these jokers actually talking about? Well, we're talking about a little bit of everything within our industry. Highlights, insights, new stuff hitting the market, big picture ideas like decarbonization, energy efficiency, how AI is going to interact with our buildings.
Well, that excited young man was Dan, and I'm Charlie. We're your hosts. Between us, we've got over 30 years of experience designing, supporting, generally selling building and HVAC solutions. If you want to know more about us, check us out on our show page, connect with us on LinkedIn. One thing you will not find on LinkedIn is how we met. Dan and I have been friends for a very long time. It all started in Mr. Halstead's 7th grade history class. And unlike that class, we're not going to bore you with the details. And it's episode number 2. Dano. What'd you think about 1?
Honestly, haven't got to think about it a lot. Had a lot going on with some personal stuff. So my son, Maverick, was skiing last Friday.
As Amber likes it.
Little Ricky.
Yeah,
Ricky
can't
Dean.
call him Rick. Listener, you can't call him Rick.
Anyway, they were skiing last Friday with your children. And first time down the chairlift, actually, I'm following Mav. I was about to get my camera out to take a cute picture of him, and he crossed the skis and wound up in a snowball. Long story short, his leg is either fractured or broke. We're still looking at that, but he's got a cute little cast on, and he's a trooper.
And now he thinks he's Iron Man.
Iron Man or RoboCop, I think.
Okay, one of the two. Nice. All right. Well, listener out there, here's what you can expect for the show today. We're going to hit some HVAC headlines, things that we thought were interesting from the week. Our interview for today, very interesting one. His name is Joe Heger. He's from our R&D team, research and design team on the centrifugal screw scroll compressor side. And then, of course, your stat of the day.
Oh, yeah.
But before we get into that, Danny boy, what is your hot take for the episode? What's your hot take for the week?
My hot take today is Project Stargate. Pretty excited about this. I think it's pretty cool. Essentially, a big private investment in data centers in the United States and really making the United States the leader in AI. So huge investment. I think that's a really exciting thing for our country, kind of talking about stuff like building power plants with data centers so we're not stressing the grid. I think we got a lot to be excited about there.
And what's the hot take?
Here's a hot part too. Another thing what I think is going to be cool is recovering heat from these places too. Now that is hot.
That's hot. That is hot. I do like that. All right.
What about you, man?
My hot take is an oldie but a goodie thing that people should be designing more around. Ran across another project today that it just needs it, and it's PIC valves.
PIC valves. You're a big PIC valve guy.
I am.
Big PIC valve guy.
I know. PIC is what we're talking about. Pressure Independent Control Valves. If you don't know about these, it's on the hydronic side. It's an easy button to reduce energy, to design better chilled water and hot water plants. Been harping on PIC valves for a very long time. And, I'm getting over there. I'm pushing that boulder up the hill. We're going to get there someday. If you're interested, please find somebody who knows about PIC valves. That's my hot take for the week, is that not enough people are using PIC valves.
And we like efficient, reliable systems, and PIC valves are a way to help us get there.
There you go. All right, listener, next up, HVAC Headlines.
HVAC Headlines, your news today.
All right, listener, here's your HVAC Headlines for the week. eGrid data updates show progress. All right, so for those who do not know what eGrid data is the emission factors that people use. So if you're interested in calculating your carbon emissions from the electricity that you use, this is the common data source that people use for it. So it would fall into this carbon accounting category. But eGrid is a way for us to aggregate up local utility grids into a larger regional grid, and then depending on what the makeup is of the assets. So is that area using coal to generate electricity, natural gas? Are they using nuclear? Or do they have a lot of renewables on? That whole asset mix comes up and aggregates into an emission factor for the region. And then if you're calculating your carbon emission for your electricity, these are the factors that you use. And so they update it every year. And so we wanted to walk through some of the updates that we saw. And so first is let's look at the dirtiest grids and, quote unquote, dirtiest grids. And so these are the grids that have the highest emission factors. Dan, you got any guesses on which grids are the worst?
I mean, if I'm going to guess, I'm going to guess upper Midwest. I feel pretty good about upper Midwest, like, Wisconsin, Michigan, Indiana.
Okay.
Iowa,
All right.
maybe.
Well, half of that is you nailed it. The other half, you're absolutely wrong.
Oh, well, educate me.
All right. No, so let's go with top three dirtiest. So number three, exactly what we're talking about, Western Wisconsin and the UP, the Upper Peninsula.
Beautiful place.
They have a lot of coal production up there, and that's kind of what drives that one. Number two is Hawaii. Number one is Puerto Rico. Both those have the same kind of problem. They're island nations. And so getting infrastructure around natural gas is really hard. And so they end up with a lot of fuel oil over the years or coal. And a lot of those are rapidly changing, especially on Hawaii. They're incorporating a lot of solar and battery production there. But those are the top three dirtiest.
It's interesting. I wonder if people would guess Hawaii on that list. I mean, it makes sense, but,
Yeah. It's just because it's so beautiful and
it's
sunny.
they got, palm trees, middle of the ocean. Okay, I don't know.
Okay. All right. All right. On the cleanest side, the other side, I would not have guessed number three. This one was way out there for me. Northern Alaska,
Didn't see that coming.
yes, has the third cleanest grid in the country. That is primarily driven, one, by not a lot of energy use.
Yeah.
And two, they have a lot of hydro plants up there to offset that. So it's renewable energy. There you go. Number two, California. Number one, upstate New York.
No big surprises.
Not a big surprise there. All right, year-over-year trends, though. Three grids had an increase in an emission rate, which is kind of interesting, right? There's generally been a big trend. The Inflation Reduction Act heavily incentivizing both the manufacture and then the use of renewable energy. So it's a little surprising to see any of these grids go up, but there's a reason for all of them. So the three grids that had an increase in emission rate were Northern Alaska, which we just said was really clean, but they don't use a lot. So any change is kind of a big impact. New York City, not upstate New York, but New York City area, and then the Pacific Northwest. So I'll start there. Pacific Northwest, the grid is called NWPP. It's everything in the Pacific Northwest plus like kind of down into Nevada, not Colorado. They had an 18% drop in hydropower from the year over year, which increased their overall emission factor by 5%.
So they're like closing down dams.
That or lack of production, right? They don't have water
the flow.
runoff to run the dam. Right?
Okay.
They have to curtail it.
Okay.
Right. The other one is New York City. They had a 10% increase in their emission factors, the biggest year-over-year increase. And it's kind of interesting because it's one of the areas of the country that people would expect to like continually drop. And I was looking into the data on this, and they had a 28%, I think is what the number was, decrease in, a 28% increase in other fuels was the category. And if you go look at what other fuels is, the three that they offer is a blast furnace gas, a tire-derived fuel, or other gas.
Tire-derived, like a wheel tire, like a rubber tire.
Yes, I don't know what that increase was from, but there you go. All right, the reason that you were wrong in your first guess on the dirtiest grids was because the largest reduction grid, take a guess, the grid that had the largest reduction in their emission factor.
Well, it's got to be Michigan or Indiana.
Michigan, yeah, exactly. 21% drop in their emission factor. 32% decrease in coal. So they basically cut a third of all the coal that was being used to generate electricity.
Wow.
They replaced a lot of that with natural gas, which has a much better emission factor. So 20% increase in natural gas, 50% increase in their solar production.
Wow. Is this year over year, like a couple years?
Yeah, it's year over year.
Wow.
Yeah, there you go.
That's a big numbers.
Michigan getting after it.
Michiganders. Go Lions.
All right, next headline. World's first grid-scale nuclear fusion power plant announced in the U.S. As it sounds, this is a big deal. If you've paid attention to the energy space for the last, 50 years, we've been talking about fusion power. Dan, are you familiar with fusion versus fission?
So I've dabbled a little bit in, like nuclear science and that kind of stuff, but I think that you should explain this for our audience. Just because it's it's pretty important. There's some big differences there, but I'll let you explain that. Just layman's terms.
Thanks. All right. So basics: fission versus fusion. The name kind of implies what it does, but fission is pulling atoms apart. Fusion is putting atoms together. So on the fission side, that's what we have today. Big nuclear reactors, atom bombs. We're using uranium in those. So you hear about like spent uranium rods or uranium enrichment. That's the technology that we use today. Fusion is the technology of the future where we're putting atoms together. We're primarily using hydrogen, my understanding, in that one, which is readily available. So it's not like it's something that we don't have a lot of. And so the promise of it, though, is on the waste and the safety side. So when you think about nuclear reactors today, there's like a big community risk aspect to it because there's the potential for the reactor to melt down and then have like radioactive material like out in the community.
Not a good
like
thing.
Chernobyl.
Not a good thing.
And the reason that's a problem is with fission, there's a chain reaction that can get away from you and melt down the reactor. With fusion, you don't have that same concern to the same level. And so it's inherently safer if we can get this technology up off the ground. And then on the waste side, you don't have the radioactive material on the back end, or nearly as much of it.
So it's a win-win. It's just a higher technological leap.
You got it. And so the headline here and why it's an interesting headline that caught my eye is the first grid-scale nuclear fusion power plant announced in the U.S. And so the company that's doing this is called Commonwealth Fusion Systems, CFS. Where they're going to put this first reactor in is the James River Industrial Center, which is outside of Virginia. It's apparently on the site of an old retired coal plant, so the connection to the utility grid's already there. The timeline here is early 2030s.
So for a nuclear project, that's like light speed?
Yeah, like I think of like the newest nuclear plant that we have in the country is in Georgia, and I felt like that one took a decade plus to complete and get the reactors up. So like fusion being out to 2030 seems like pretty fast. I don't know, or early 2030s is what it says. The size of it is 400 megawatts, which is about the equivalent of the electricity of 150,000 homes annually.
Is this technology like a scalable? Like will we see like little guys, or is they making big ones? Or
yeah, I think both.
Like the first one.
Yeah, no, if you can figure out the technology, I think it's scalable up and down. I think fusion is still in the scale of proving net energy, which means they're able to sustain the reaction long enough to generate more energy than what they put into it. So I feel like that's still the stage that we're at. If you know more about this and you want to educate us, reach out, coolair.hottakes@trane.com. But that's my understanding is like we're still pretty early in the technology, and having this announcement seems like it's progressing rapidly.
I think it's cool. I mean, it's obviously if you want to do this whole clean power thing, this technology has to play a role.
I agree. I think it's very interesting.
Awesome. Well, next up, we have our guest interview with Joe Heger. He's a centrifugal mechanical engineering leader at Trane. He's going to talk to us about compressors and bearing technology.
Hey there, listener and building owner and facility manager. Are you struggling to retrofit your hydronic systems with heat pumps? Do your sustainability goals seem out of reach? Trane might have an easy button for you. Introducing Trane's Hydronic Branch Conductor, part of Trane's comprehensive chiller heater system. This game changer slashes the cost of installing coils, valves, piping, and joints by using deep dual-purpose coils, unlocking low-temperature heating. Go to trane.com/conductor now for your free quote. And now, back to the show. All right, listener, welcome back. We have a very special guest for you. And if you are hearing this, it means that we have gotten approval or we have edited out all of the trade secrets that Joe Heger shared with us. So welcome to this show, Joe Heger.
Thanks, Charlie. Glad to be here.
You're welcome. So a little bit of background on Joe. Besides being a very handy person, listener, if you're out there and you need a home improvement project done, Joe's your guy, 608-397-9944. I'm pretty sure that's your number.
675-309. That's what I thought. Right.
Joe is one of our lead engineers around the R&D for our advanced compression technology. So what's coming in the future? What do we have today? And we brought him on the show to talk kind of a little bit of the past, present, and future around compressor and bearing technologies. Before we get into that, the show's called Cool Air Hot Takes. So what's your hot take? This could be anything in the industry. It could be compressor related. It could be personally related, anything in your world, what's your hot take?
So my hot take, because the intent here is to talk about bearings, it's bearing related. And so the hot take is that you should never fall in love with a bearing technology.
Have you ever fallen in love with the bearing technology?
Have you been burned?
I fell in love with probably rolling on with bearings once.
And how'd that go for you?
So the rationale behind the hot take is, as a compressor engineer, we got to stay objective when it comes to selecting the right bearing technology. At Trane, we're agnostic when it comes to bearing technology. We don't go out and say this is the best because it's highly dependent on the compressor type and the application. We always want to make the right choice. So you have to keep an open mind. And if you fall in love with one of them, that you don't want to make these decisions with your heart. You got to make them with your head. So that's one. And I guess the other reason is, every bearing technology eventually will hurt you and hurt you deeply, right? So, if you select the wrong one because you're in love with it, it is going to hurt you, in the end. So you do have to keep an open mind and not get too attached to any of them.
Spoken from real experience. I like it.
So, Joe, why don't we start with a little bit of background? Where are you from? How did you get into compressors?
Oh, boy. So the quick is I'm a farm boy from North Dakota. So I grew up on a farm. That's probably where the handiness comes from. And took an aptitude test in high school, said I should be an engineer. So I went and became an engineer. I mean, it's not the most exciting story in the world.
That is a very engineering start, by the way. You take a test,
served me well.
It tells you to go do this, and you go do it.
Right? It told me what to do, and I went and did it. Right? So that's the simple story. But yeah, and had a lot of opportunities coming out of college, and Trane ended up being the one that looked the most interesting. And that's been the right choice, man. It's been 25 years I've been doing this. And never had a boring day, I'll tell you that much.
All right. Well, we're going to start way, way at the beginning here. To ground everybody, to help us where we're going in this conversation, what was the first compressor? What were the first forms of this technology?
Well, in the beginning, it was a bellows, right? For a forge, in BC times. Those were the very first compressors.
All right.
So if you want to go way back that far in compressors. But
I see what you're saying. Yeah, compress the air.
Yep. But if we want to talk about modern compression, we're probably in the 1600s, 1700s, where piston compressors were used for air.
Yep. So for the listener, that would be like an engine in your car.
Yep, exactly. Yeah, there's a piston and a cylinder that's pressurizing a fluid. But, for air, the actual vapor compression cycle for refrigeration didn't really come around until probably I think it was the 1600s or 1700s it was conceived. They didn't know how to do it. And so it was the 1700s when the first systems started to be used that would actually use a compressor. And at that time, I believe they were piston compressors.
When did the broader industry kind of move away from reciprocating and into our new technologies, which we'll talk about?
Probably in the 70s, I'd say, is when we started to move away from that. That's when both scroll compressors and screw compressors started to enter that space and really disrupt the reciprocating compressor space.
So what was that disruption?
Despite the color of my beard, that was before my time. I believe it was mainly efficiency. In a reciprocating compressor, you have tons of pistons, tons of bearings, you have lots of losses, lots of pulsations and those types of things. And then some systems like a scroll compressor or a screw, which when done right can be very efficient and very cost effective. And I think they just became a better solution. They were just a better mousetrap at that time.
You mentioned bearings in there, and I think compressors and bearings, although they're not really mutually exclusive, they do come along for the ride with each other. Bearings have grown in their importance, or at least their perceived saleability in our industry over time. What's the technological arc, or what's the technology arc for bearings look like over the past, 100 years, or not even? You probably don't even need to go that far back because roller element bearings.
I will go back to BC this time. I mean, too far. But I would say, first of all, every compressor has to have a bearing, right? Something is moving, something's sliding, something has a load. So that's kind of the definition of what a bearing is. So every compressor has a bearing. And I'd say the first bearings that were used in systems were either hydrodynamic bearings, like a sleeve bearing, where you just have a shaft inside of a sleeve with oil, and that supports the load, or rolling element bearings, where you have ball bearings. Those were probably the early ones we saw.
Before we go too far down the bearing path there, can you give us an idea of present? So today, what are the compressors? What are the bearings? What are the applications that we have today?
Certainly in the scroll range at the very bottom end of capacity, from a few tons up to maybe 30, or there's some bigger ones that are out there too. That's the range that scrolls would cover. The bearing types they use are typically some type of a bushing that's in there. And then they have a flat plate thrust bearing typically within the scrolls. And you would select, and the reason why they're popular there, frankly, one of the big reasons is cost. They're really a very solid efficiency in that capacity range. They're very robust and just really, really good little compressors for that faster and very suitable for mass production.
And then you said bushing or roller element bearing on there. Why would you not put a mag bearing on something like on a scroll compressor?
Probably the biggest reason, one is just footprint. Mag bearings are gigantic, and you'll probably touch on that in a couple other bearing compressor types.
What's gigantic? Like, yeah, if you say like, if I'm thinking of a roller element bearing in my mind, like how many times bigger?
5 to 10.
Oh.
Right. Yeah. much, much larger. You know, the footprint of for one application we've looked at, that's about the diameter of a rolling element bearing that we sized for an application. If we're looking at the same application for a magnetic bearing, by the time we're done, including the thrust bearing, we're probably this big.
So for the listener out there, we're going from
much
Joe's,
more space.
Joe's showing us with his hands.
I know, I'm off the screen.
So it's from like a 4-inch to a 12-inch.
Yeah,
diameter.
I mean it's 3, 4, 5, 6 times the size.
Got it.
So, and it's because their load capacity is per square inch is the way we look at bearings. You know, it's if you just project the area of a bearing, how much PSI loading can that take? And the PSI loading capability of a mag bearing is fairly low. So they have to be big to cover that. It's like having snowshoes, right?
I would assume cost has something to do with that too. Like I'd assume a scroll compressor is a lower cost design.
Yeah, that's probably the another reason too. One is it's nearly impossible to fit them into a scroll compressor unless you totally radically change the design. But on top of that, it's really cost.
Would that be the same for a screw compressor?
Yes. Yeah, it's the same. It's also packaging in a screw. And it probably in a screw compressor would not have the load capacity. Even if there was a way to do it, screw compressors tend to have fairly large loads and have very, very precise requirements for locating the screw rotors. That's one of the reasons that we use a rolling element bearing is because they're very, very good at keeping a shaft in a very precise location.
Yeah, can you give us an idea? And we might have to cut this, Joe, but
yeah, that's okay.
Now I'm curious. How tight of a tolerance can a mag bearing keep a rotor shaft versus a roller element?
100 times.
Huh.
So because a rolling element bearing is preloaded, it's pressed into place, and there's oversimplify it, but metal contact from the housing all the way down to the shaft. There's a film of oil between the rollers, but very, very precise control. You can control within a magnetic bearing. You will have just in the air gap that you have, and then outside of that, you have usually some compliance that'll allow the shaft to move even more within that compliance. And so the range of motion that you get within a shaft that's using a magnetic bearing is much, much higher than you would see with a ball bearing.
Got it. So we can move into centrifugal now. Like centrifugal, we typically use in large capacity, but I feel like that's starting to change. I feel like we're trying to apply centrifugal compressors kind of up and down the capacity range here. So what's the allure of centrifugal compressors and why are we trying to use them basically on almost every product line?
When we look at it from a capacity standpoint, when we go to high capacities, it's really the only option that we have. There's no other technology out there that can do it. And I'm talking probably 500 tons above in just our standard comfort cooling terms. And so above that, there's just not much else out there that can really compete with it. When we get into the lower capacities of 500, all the way down to single digits even, then you're in this area that we call the battleground, where you've got screws and centrifugals fighting for the same spot. You've got screws, centrifugals, and scrolls, maybe even some recips down in like the 50-ton or 30-ton range that are kind of duking it out. And the reason a centrifugal is starting to push down further and further into that range is a couple things. Efficiency. You can get a little more efficiency out of a centrifugal in that, than you can with those other positive displacement options. The other thing that we see is trends in refrigerants may favor a centrifugal over a positive displacement. And then third is it's really the only option that you have if you want a system that's oil-free. So if that's a customer requirement, that's something that they want, it's also a big plus.
So just to connect the dots there, oil-free meaning magnetic bearing can't put them on screws and scrolls today.
Correct. Yep.
Got it. Yep. All right. So it's kind of the past and present.
Mm-hmm.
Can you give us a little bit about the future, where we're headed with compressor bearing technologies? Two areas that I think are really interesting in this space. One is energy efficiency. And where are we going to find this energy efficiency? Is it innate to the technology that we can continue to progress, or are we going to look at new technology? And then the other side is electrification is a big trend in our industry. What does that do for compressor technology? Where does that drive us to?
Mm-hmm.
So those are the two questions I have. Let's start with efficiency, though.
Yeah, there's a lot there. So efficiency. I think my answer to the efficiency question, I think you're asking it about compressors specifically, right?
Yeah, either or. Yeah, I guess if there's like massive gains to be made in the bearing side, like sure, go there.
Yeah, well, I'd actually go the other way. I'd take it to the system level, right? Because our customers don't buy compressors from us, or I'd say the end users that buy this equipment, they buy systems, right? So we sell system efficiency. And so the compressor
system being
a chiller or a rooftop unit or something like that. So that's the product that they buy from us.
It's the piece of equipment that is making some things hot or cold.
Correct. Yep. So that's what they're looking for. I guess the one thing I'll say is when it comes to efficiency, we're not near peak efficiency, right? We have efficiency, it's on the table. And usually the efficiency that we put into a system or a compressor is kind of dictated by whatever the customer is willing to pay for, because there's a relationship. If we can put better materials, better finishes, higher grade motors, fancier bearing technology, more heat transfer surface into a system, we can make them more efficient. So, I'd say across the board in our systems, we're not at peak efficiency. We have more that we can do. It's just a matter of, I would say, what's commercially viable.
Yeah.
Right.
Without giving away, percentages or more orders of magnitude here.
Mm-hmm.
Well, that's exactly what I'm asking.
It's not orders of magnitude, right?
How much is out there? Like, how much do we know is on the table?
These are things we've done a long time ago, but, if we take a system and just throw everything at it, we can be 10, 15% more efficient on full load if we really need to. That's possible. We've seen that.
So, Joe, one of the big trends in our industry right now is electrification. And a lot of the projects I work on, they're asking for higher temperatures, higher pressures, even getting into steam and looking to replace some of those systems. Where are we driving with our compression technology in order to meet some of that market demand?
I can't probably talk about everything that we're doing and that we have in development.
No, you can't. Yep, you can. It's a safe space here.
Yeah. Like I said, it
nice.
feels very safe.
Safety tree.
But I can't describe what we see in the industry. Right. So we see the same types of compressors being used in high temperature applications. So we see centrifugals, we see screws, we see scrolls, we see recips. And so it's not necessarily a matter of finding a new compression technology to use the vapor compression cycle for heating. It's more a matter of finding the ways to take that equipment and either existing designs and harden them for that higher temperature application, or optimize them and create new designs that are truly optimized for that. What I see in industry right now is people taking existing compressors and just running them really high temps, stuff we hear through the grapevine that's not going so well. And so you're starting to see the people like us. We have launched one product in EMEA with a screw compressor where we've done this. So that is out in the public domain, but where we've taken an existing screw compressor, we've done the hard engineering behind it to get the right materials, the right lubricants, the right application, and turn that into a reliable high-performance product. So I think you'll continue to see that. And bearing technology is a big part of that, because as we go to these higher temperatures, it does stress bearings, it does stress lubricants, and those are really some of the bigger challenges that we have when we get into these really high temperatures.
All right, Joe, last question for you here before we depart. So our last guest, we interviewed, his name was John Horn. He's the managing partner at the Idea Fund, which is a venture capital firm. We asked him for a hot take. We're going to ask you for a hot take too here at the end of this.
Sure.
But his hot take was that the HVAC industry is ripe for massive disruption over the next 5 to 10 years. Okay?
Yep.
Assuming that is true, what technology on the compressor or bearing side do you think has the potential to do that for us?
The biggest disruption, I'll go to the bearing side on this, is I don't think we've talked a lot about gas bearings yet. A gas bearing is another bearing technology where the shaft actually rides on a film of gas. And it's either something that's generated by the rotational motion of the shaft, as in a foil bearing, or it can also be pressurized, where you insert pressurized gas into the bearing and it levitates it that way. That technology is particularly useful for very small, very high-speed compressors to make them more efficient and also to make them maybe a little more cost-effective, because magnetic bearings are still expensive. And so that gas bearing technology is enabling kind of a generation of ultra-high speed, small capacity centrifugal compressors that I think you're going to start to see in applications all over the place. And for the reasons we talked about before, it's efficiency, it's oil-free, it's sound, it's footprint. These compressors are much, much smaller than the technology that they're competing with.
Yeah.
That's exciting. That's super cool.
All right, Joe. Appreciate your time. Thank you for joining the show.
Thank you.
Have a great day.
It's been a blast. Thanks, guys.
Ever wonder what a successful hydronic heat pump system in a cold climate looks like? Curious about real-world heating and cooling systems? Well, you're in luck. Trane believes electrification of heat challenges can be solved, and they're leading the way with their own facilities. Visit the world's first thermal battery storage source heat pump system at the new Trane Customer Experience Center in La Crosse, Wisconsin. See real-world electrified heating that works even in cold environments. Come see the future of sustainable HVAC today. Contact your local Trane account manager to schedule your visit. And now, back to the show. All right, before we wrap up the show, let's hit the stat of the day.
Here comes Joe.
Stat of the day.
Stat of the day.
Stat of the day. And today's stat of the day is looking at which countries have the most data centers.
Oh, yeah.
Let's look at this list. I think this is pretty interesting. Let's just start with number one. The United States, almost 5,400 data centers. It's kind of crazy. Now, it's going to get crazier when we look at the rest of the list. Number two, Germany, 521. Number three, the UK with 514. Without going down the whole rest of the list, you can add up 2 through 25, and you're still more than 400 data centers short compared to the United States.
It's a bit of a lead.
Kind of wild.
It's a bit of a lead.
That is wild.
My guess is there's a couple countries in here that start with a C and an R that probably aren't reporting to the same levels, but that's a pretty impressive gap there.
That is very cool. Now, take on that whole Project Stargate's going to make that gap even bigger potentially.
Well, yeah, no, if you think of like the long-term effect, right? Like we're already at a head start here. We're already consuming massive amount of energy, and like the projection for where this industry is headed is mind-boggling in terms of the amount of energy that we're going to need for it.
The future's like pretty exciting. I think our industry is super cool, super fun, and I think that's really interesting.
Geeking out.
I am, I'm sorry. Let's wrap this up.
All right. Thanks for listening to this episode of Cool Air Hot Takes. We've been your hosts, Charlie and Dan. Next time, our guest is Ray Reiling from Tradewater. Tradewater does refrigerant destruction in order to create carbon offsets that people can use for their Scope 1 credits. So very interesting, kind of a niche topic in this broader world of refrigerant. So we're going to bring you all sorts of content around refrigerant. We're going to call the episode Refrigerants. So we're going to have plenty to say about refrigerant on both sides of the fence. But if you want to get in touch with us, drop us a line, coolair.hottakes@trane.com. We want your rants. We want to hear what you have for questions. We want to hear what you have for hot takes. Anything funny from the jobs you've been working on, any funny stories, please reach out. We'd love to feature it on the show.
If you like the show, please like and subscribe, give us a rating and a review wherever you listen. And until next time, stay cool and keep those takes hot.